Yes, hello everyone. Yeah, so thanks for coming to the AMD event. And yes, I'm going to talk about the future of training and reinforcement learning. I'm from Unsloth. I'm Daniel. My brother's also here. And check us out. And we kind of just supported AMD training via Unsloth, so definitely check that out as well. So you might know me or you might not know me. I'm a Twitter person. I post a lot. So last year we fixed a gradient accumulation bug. So essentially all training frameworks had this problem where gradient accumulation was not done correctly. And so we helped fix it in transformers, PyTorch, everywhere. We also introduced something called async offloaded gradient checkpointing. So essentially the trick is when you do gradient checkpointing, you don't actually put the memory on the GPU. You can actually move it to RAM, so system RAM. The problem is, though, there is like 7% overhead. So we can like get rid of that overhead entirely by using asynchronous operations. We also did something where we fix bugs in open source models. So for example, we collaborate with Hugging Face, Google, Meta, Mistral to fix bugs in open source models like Gemma, Llama, Mistral, and Phi. So the open source models that you guys probably use or try out have our bug implementations. And also follow me on Twitter. I post all the time about the latest AI research, reinforcement learning, bugs that we find. So whenever you try a new model, we'll post about, there's this bug in this model. And so we will try to help fix it for the community. For example, Microsoft's Phi model, we helped identify that the chat template was a bit there were some issues with the chat template, so we helped fix it. It does increase accuracy during inference by a few percentage points. We also helped collaborate on Llama 4, for example, fixing some issues as well. So definitely do download Llama 4. We helped increase accuracy quite a lot as well. And yeah, we found the model to be quite performant. We also upload quantized versions of these models. So Llama 4, you can actually fit on your local device, and it works very well. So Phi 3 bug fixes, Phi 4, we also work with the Quen team before they release. And we also, I don't know if you guys know, but Mistral released a reasoning model a few days ago called Magistral. We helped partner with them before their release to release Magistral for them. And yes, we just surpassed 10 million monthly downloads in Hugging Face. We have 40,000 GitHub stars now. And we collaborate with all the large model lab teams before they release a model. So definitely check us out on Hugging Face. All models are for free to download on your local device. So definitely check that out. And we have a GitHub package. So this is actually our main offering, which is we provide fine-tuning and training via Unsloth. We have around 40,000 GitHub stars. You have access to free GPUs via Google Colab, Kaggle. And AMD announced they have an AMD Developer Cloud. So if you can sign up for AMD Developer Cloud, you can use Unsloth via that as well. And we have notebooks for continued pre-training, supervised fine-tuning, reinforcement learning, and much more. Our Hugging Face page, we also upload dynamic quants. So this is where you can run these on your AMD GPUs, NVIDIA, any single local device. It works very good on AMD GPUs. It's extremely fast. And we essentially provide bug fixes to all of these models as well. And all of these models that we upload can run on your local device. So for example, DeepSeek R1, so DeepSeek R1, you can actually run it on your local device. Although it's 671 billion parameters, you can actually load it on your computer. And the trick is you do something called offloading, where you offload all the MOE experts to system RAM, and then it can put it back into the GPU over time. So you don't actually need to load the entire model into your GPU. So if you don't have this gigantic GPU, it's not necessary. You can actually load up in your local device. So if you have a local AMD GPU or a general GPU, you can actually load the entire model onto that GPU, and it's pretty good. But today I'm going to talk about open source models and reinforcement learning in general. So I don't know if you guys saw this graph, but it shows the performance of closed source models and open source models. Open source models is the green line on the bottom, and closed source models is the red line. So this is pre-reasoning time. So this is before reasoning models came about. You can see that open source models definitely caught up to closed source models. And the view is the slope of open source models, the development progress is much steeper than closed source models. But this is pre-reasoning phase. In the open source community, we like to talk about two phases of model releases. We call this the SFT, or the RAHF jump, which is when ChatGPT got released. I'm not sure if you guys know, but before ChatGPT, there were language models, but no one really used them. And why is that? Because they were not trained correctly. It was just like base models. It wasn't really instruct-tuned correctly. And then ChatGPT came along and showed that if you have good data, if you can train it correctly using SFT and reinforcement learning with human feedback, you can actually have this gigantic jump in performance. And that's why ChatGPT was very popular. The open source models are like the blue line, and there is like a delay, right? All the time there's like some sort of delay between the closed source performance and open source performance. And then we call this something called the OSS drought. Around September 2024, O1 got released by OpenAI. And then open source had this like reckoning moment where there was like no model which could perform as good as O1. So there was like 4 months of a gap, and we call this the OSS, well, I call it the OSS drought. But then suddenly DeepSeek R1 came along and revitalized the entire open source community. They showed that actually closed source models can do fine, yes, but open source models can also do very good if you use GRPO, RL, and the DeepSeek team showcased this through R1. And so like now, open source models and closed source models are pretty aligned in terms of the performance. And we call this the RL jump. So the secondary jump in performance is the RL jump, where you do reinforcement learning to increase the performance of all these models. And that's what I'm going to talk about. Also, there's something called the MLLU plateau. If you see like benchmarks and stuff, MLLU is generally standardized across all models. The performance is not going to change that much, right? It's already like 90%, 88 to 90%. But the capabilities of the models keep increasing more because of this RL jump. So I like to frame it in another way as well. My view is like we call it fine-tuning is everywhere. Right, we start off with pre-training, where you pre-train a model, right, like 30 trillion tokens, right? You pre-train a large model like Llama, and then you do the SFT phase, which is called supervised fine-tuning. This is where you have like chat data to make the model more, you can follow instructions. And then finally, we have the post-training phase, which is like making the model more performant and more aligned to what you want to do for the use case. But this is like the 3 main categories of the phases of training. But I actually like to break it down into more phases. So there's like more terms now. So pre-training is still here. So people will pre-train large models. But then there's something called mid-training, which the Twitterverse likes to talk about. And mid-training essentially introduces more high-quality data after pre-training, or like during the pre-training process. You could do long context extension, higher quality science data, and so on. And then we still have the supervised fine-tuning step, which is like make the model more instruct-aligned. And then we have preference tuning, which is like DPO, RAHF, which makes the model more aligned with good and bad responses. So in ChatGPT, if you see the thumbs up and the thumbs down, the models get more aligned to produce the thumbs up ones and get reduced chance to do the bad ones. And then finally, we have something called RLVR, which is this new phenomenon called reinforcement fine-tuning. OpenAI likes to talk about reinforcement fine-tuning a lot. And RLVR essentially is a new phase where you can train models to do reasoning and with verifiable rewards. And so this is like a new phase that everyone's talking about currently. And the purpose of these models is you have like a base model, like GPT-4 base. So actually, GPT-4 is not a base model. It's a fine-tuned model from GPT-4 base. Claude 4 Opus is like a fine-tuned model from Claude 4 base. Right? There's actually a base model somewhere sitting on their servers. I don't think OpenAI will ever serve the base model, but it's somewhere sitting there, and they have to fine-tune it to make these models. So another way to describe it is this diagram that I like to talk about. So essentially, my view, like the view of AI currently is kind of like an optimization problem. Right? You start off at the very bottom left corner called the pre-training, the random initialization phase. It's like the black dot. Essentially, all the weights in the model are like random. And then the goal is you do gradient descent, backpropagation, you learn over time. You go in this like big 1.4 trillion parameter space. You move around. And then you go into the pre-training phase. Right? You like finally get this pre-trained model, which does much better than the random initialization. And then you have to do extra steps, like the SFT phase, or the instruction fine-tuning phase. And then you have to do preference fine-tuning. And then you do RLVR, which is reinforcement learning with verifiable rewards. There is a new trend going on in the community where you can actually skip the top area, which is the generic method that you do. You can get the pre-trained model and skip directly to the RLVR phase. And this is like DeepSeek 0 and stuff like that. You don't need to go through the SFT phase and stuff like that. And you could just bypass it. This is like a new trend in the open source community. So essentially, what is RL and stuff? So this is a Pac-Man game. So you are the yellow character, the yellow dot, right? You have actions of going up, down, left, and right, right? That's your action. You can only choose 4. The reward is the little cookies or the food that you can get. If you can eat a cookie, you'll get +1 reward, right? But if you hit one of your enemies, then you get minus reward. And so the goal of RL is, given this environment, how do we maximize reward? And that's just RL, right? And so the goal is to write this environment, let the AI agent go inside this environment, and maximize reward. Another way to think about it is the goal of RL is we want more good and less bad. For example, you ask a model, what is 2 + 2? Right? The answer is 4, obviously, right? It's 4. Let's assume the model says 3, right? Let's say the model says, what is 4 + 4? What is 2 + 2? It's 3, right? Clearly, it's wrong, but it's much better than if it says B or D, right? Or -10, right? And so the goal is with RL is, given bad answers, you want to penalize these bad answers, and you want to reward good answers like 4. The more architectural view is, for example, OpenAI's GPT-4 is trained using PPO and RLHF. It's like this more complicated design where you have the training data with this like AI agent. The AI agent is just a language model. And you have like 3 different components of the language model, right? The generating policy, the reference model, and the value model. And you also have this like reward model. And so this is kind of the framework of how OpenAI trained the model. By using this training, we can essentially try to optimize this approach, right? You want more good and less bad. And so essentially, RL is kind of like this luck searching algorithm. For example, at the very beginning, you ask the model, what is 2 + 2? It might say, 10,000, right? But then you keep calling the model. What is 2 + 2? What is 2 + 2? What is 2 + 2? It might say 3, 2, 1, -10, A, B, C. I don't know which one, right? You call it 10 million times, and then suddenly, just by luck, 4 comes out, right? And 4 is the correct answer. And so you will reward this, right? You will +1 to the reward. And so the model now understands, oh, OK, 2 + 2 is 4. Let me optimize the model weights to make 4 appear more. And that's the goal of RL. Essentially, reward is like 0, 0, 0, 0, 0, 0, right? Every single time the answer is wrong, 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 and then suddenly the answer is correct. And that is the whole point of RL, right? The whole point is to do inference as long as possible, and by chance, by luck, you'll get the correct answer. And by doing this optimization process, you'll get a final model which is very powerful. GRPO is what DeepSeek showed. That is a more efficient version of PPO, right? You don't actually need to do this entire process of like having many different components. They delete the value model and replace it with like a reward function. They delete the reward model. They delete the value model as well. And there are like new methodologies called LLM as a judge, regular expression checking, format checking, executable code. There's many things that you can do to reward the model, right? Like instead of just saying what is 2 + 2 and the answer is 4, it doesn't have to be a math question. It can be anything, right? It can be, oh, did this legal case win or lose, right? It can be like something like that. In terms of RL in general, we have like many, hundreds of notebooks that we share for you to like learn how to do reinforcement learning, fine-tuning in general. We showcase that you can actually do reinforcement learning on a base model, on Quen. And so like we showcase that you can actually do a format. Reinforcement learning has a tendency to just do formats. So the trick is to bypass reinforcement learning, trying to like just follow the format. You can do SFT first, which is fine-tuning a little bit of the model, and then you can do RL, and it works very well. So there's many notebooks that we have which showcase this, showcase how you can do RL. We also just supported AMD GPUs, so definitely check Unsloth training on AMD GPUs. We're trying to make the installation process a little bit better, but essentially you can run large training runs using Unsloth on AMD GPUs. And also, as I talked about, the quantizations that we do also. So essentially, you can run DeepSeek R1 on your local device. We showed actually that we quantized it all the way to 1.58 bit. So previously, the model was like 700 GB. We compressed it to 150 GB. And the performance is fine. We actually find that if you compress the MOE layers to lower precision, it actually does fine. So you can actually compress the MOE layers all the way to like 2 bit, and it's fine. but you must leave the attention layers in higher precision, like maybe 8-bit or 6-bit. And you can see, like an example, we told the model to generate a Flappy Bird game, and the the dynamic 1-bit version still manages to generate the Flappy Bird game with good, it works very well. There are like some issues, like sometimes it might get a Python variable name wrong, but generally it works pretty well. Llama 4, for example, we showed that if you quantize Llama 4 down to very low bits as well, the accuracy doesn't really degrade that much. The plot is a little bit, the axis is not very good, but if you see a bit more clearly, the axis is only like 2% accuracy difference. So the smallest quant, the smallest model that can fit on your local device still runs relatively well. So this is Llama 4 Scout, and it works pretty good. And we also show Gemma, so Google's Gemma model. If you do dynamic quantization as well, you can actually increase accuracy as well without losing any performance as well. And the model is also smaller to run. For example, there's a comparison of performance. The first dark green line is the quantized version that we serve for, I think this is Llama 4 Scout. And then the secondary dark green line is inference providers. So actually, our accuracy is actually higher than actual inference providers, primarily because of we quantize using our dynamic methodology, which quantizes very well. We also fix bugs in the implementation. And so if you do run local models, Llama 4, definitely give that a try because the accuracy is pretty good. And so for example, another view of quantization is this picture, you have this picture, it looks like a train, right? You ask the normal model, what is this picture talking about? And it shows, this image shows a train traveling on tracks. Right, that's good, right, very good. And then you quantize it to 4-bit. And then what does it say? It says, this image depicts a vibrant and colorful scene of a coastal area, right, which is totally wrong. Why? Because you're not supposed to quantize every single layer. If you quantize every single layer, the model becomes dumb. And so the trick is, which layers do we not quantize? That's the question. And so what we show is you can still you leave some layers in higher precision. The question is which one? And then the answer is good again, right? This image shows a train traveling on tracks. So it recovers the accuracy back. Oh, also, so thank you a lot. We do have stickers after the talk. So we have some stickers if you want to grab that out. Definitely start us on GitHub and check us out. Okay, there's 40 seconds left if you guys have questions, but thanks a lot. Questions? No? Oh, OK.
Hey, Daniel, great presentation. Thank you. This quantization is so exciting, right? Like you showed, if we know which layer to quantize and then bring it down, and if the accuracy stays, I mean, it sounds like a win-win situation. Is there some catch we should be worried about? Is it maybe it doesn't generalize as well, or because I guess the question is, why don't every model just become that nice hybrid, quantized models?
We do know most likely large model labs are probably going to do something like this, where they can quantize some specific layers and don't quantize every single layer. It does increase throughput. It makes the model run faster. You can serve many more people. It does generalize. So we find that most models, because they use a transformer architecture, you don't need to quantize every single layer. Attention needs to be in higher precision. The MLP layers can be lower precision. It's not that serious. So generally, it does generalize across models. For example, we found it to work well with Llama, DeepSeek, Qwen, Llama, Mistral. So many of the open source models seem to do fine with quantization. So it definitely does generalize.
Great to hear. Thank you.
Yeah. Any other questions?
Maybe I missed this, but how did you decide which layers to quantize and which not? Is it an automated feature that?
Yeah, so we do have a blog post about this. So what we essentially, there are many papers which showcase this. For example, there's a paper called the superweights paper, which shows that just one number in the whole model, just literally one number out of 1.4 trillion parameters is very important. And this one number, if you quantize it, you will reduce the accuracy by 50%. So the question is, where is this one number out of the 1.4 trillion parameters? So you have to find that. So for example, you could this is a very dumb solution. You could set it to 0, and then see the accuracy, right? Every single number you select, OK, set this one to 0, set this one to 0, set this one to 0, check the accuracy. And you see, oh, OK, this number seems to be very important. And so you don't quantize that, for example. And so we do something like that. OK, it's more efficient than that. Obviously, like you shouldn't check all 1.4 trillion parameters. That'll take forever. So there is like more efficiency baked into this stuff. But that's kind of what we do. Yeah.
So do you do anything with quantization to reduce the weights for the layers that aren't, sorry, not quantization. What's it called? That NVIDIA does, the sparsity, not quantization.
Yeah.
Do you do any sparsity on the layers you can't quantize to reduce the weights even further?
No, we do not introduce sparsity. So the lottery ticket hypothesis paper is probably very good for this, where you like you finish training the model, and then you like sparsify the model. Generally, interestingly enough, quantization kind of introduces sparsity, kind of. So essentially, during the quantization procedure, there will be more zeros into the model. So we don't do this like forcefully. We just let the quantization procedure do it. If that makes, yeah.
Well, no, the layers where you can't quantize, they have to stay in high precision.
Oh, OK. If they stay in high precision, we do not do sparsification. We just leave it in. I mean, you could do sparsification. You could. I think for engineering, it's probably going to get too complicated to sparsify. So we just leave it, like a dumb trick. Oh, OK, it just works. So we don't sparsify it. Yeah. Any other questions? Or no? OK. Thanks a lot.